Mr. Bennett has a job of explaining the nucleus, so that's what the first part of lecture 2 is about. We're going to start talking about the electrons. Essentially, all you really need to know to talk about the electrons is there is a nucleus. It's tiny. It's in the center of the atom. It's got a positive charge. And then you've got electrons around it. So people were more interested in, some people were interested in what's going on in the nucleus. That's how we got nuclear power and nuclear weapons, etc. But chemists are mostly interested in what's going on with the electrons, because electrons are what bump into each other when atoms meet each other. So electrons are where all the chemistry happens. Electrons can get transferred, electrons can get shared, etc. So chemists, physicists wanted to figure out, right, where are the electrons? What are they actually doing? And that was non-obvious. It took a while to figure out. One of the ways that we got information about the nucleus, or about the electrons, was to give atoms lots of energy and see what they did. And so they'd shoot out light at certain energies. People tried to figure out, all right, what does that mean that they're putting out light with specific energies? So I'm going to explain essentially the theory, and then we'll talk about afterwards light and how light gives us evidence for what's going on with the electrons and atoms. So the first real description of the electrons was the Bohr model. So anyone remember what the Bohr model was like? It's also called the planetary model. Yeah, so what Bohr's model was that the electrons followed a specific path. They followed circular orbits around the nucleus. And each orbit was at a specific distance. They were like tracks. And an electron could be on one track, or another track, but it couldn't be in between tracks. So he essentially said you have a nucleus in the middle, and then you've got these rings around it. And you could have electrons traveling on that ring, or you could have electrons traveling on the next ring, or you could have electrons traveling on this next ring. And they just had to be in those fixed orbits, going around in a circle, like planets around the sun. So that's where the planetary model name came from. And so this had some advantages. This explained why electrons only give off certain wavelengths of light when you heat them up, and that's an explanation that we'll give later. But it explains certain phenomena, and visually, it's actually a nice picture for us. When most people picture an atom, they picture some version of the Bohr model. That symbol where you've got the nucleus in the middle, and then you have like circles going around it. What most people picture when they picture atoms. So the Bohr model has this advantage that it's easy to picture. It explains some things, the idea that electrons are an energy level. Now, why would these different orbits represent different amounts of potential energy? All right, well, each one could have a certain amount of electrons in it. Yeah, that was part of his model, was the first ring could hold 2, the second ring could hold 8. But why would the second ring have a different potential energy from the first? farther from the nucleus. So remember, electrons are attracted to the nucleus. So orbits that are further from the nucleus, because there's an attraction, they would be at higher potential energy. So each orbit was like an energy level, and the further away you got, the higher energy those electrons had. So it has advantages, and we'll use the Bohr model pictorially a lot, just because it's simple for us to draw, it's simple for us to think about. But it turns out there are things that it can't explain. And so, like with any theory, when you run into evidence that says, yeah, this theory can't explain this evidence contradicts the theory, you have to say the theory isn't right. Just because the theory isn't right doesn't mean we can't use it. Doesn't mean it's not useful in a lot of simple applications. So we will still use the Bohr model, but recognizing it's not perfect. Similarly, technically, Newton's law of gravity, well, it's not quite right when you consider general relativity. There's a more complicated theory that's replaced it, but we still use Newton's law of gravity because it's simple enough for us to understand, and it works in a lot of situations. So we will use the Bohr model when it works, but it has problems. So some of the problems with it. One, if you know physics, and you know that anytime you have a charged particle that's accelerating, it gives off light. Well, anything moving around in a circle is constantly accelerating. So if electrons were doing this, they would have to constantly be giving off light. And if they were constantly giving off light, they would have to constantly lose energy. And if they constantly lost energy, they would spiral in towards the nucleus. Okay? So this model didn't make sense. Bohr didn't have a way to explain why the electrons didn't crash into the nucleus. So it can't explain why the electrons don't just fall into the nucleus. Also, because it makes these circular orbits, it can't really explain the shapes of molecules or the shapes of different chemical structures, because everything would just be circular. Every atom would just be spherical, essentially. So it can't explain the shapes of molecules and other structures. And then another big one is actually this deeply theoretical one that I'm just going to introduce the concept. It's not something you really need to understand, but it violates what we call the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle, essentially, Heisenberg showed that you can't actually measure where a particle is and where it's going at the same time with perfect precision. So there's always going to be some uncertainty as far as where particles are. And having a model where particles are in a fixed orbit going at a fixed speed, because Bohr's model predicted, all right, in order to stay in orbit, it has to have this certain speed, violates that, because it's saying you know exactly where the electrons are. Electrons are in a specific place, and they're moving in a specific direction. So the Heisenberg uncertainty principle essentially says You can't measure the location, so the position, and the momentum of a particle. So there's always some uncertainty. For big objects, it doesn't really matter. So if you try and measure the position and the velocity of a car, the uncertainty can be so small that you can ignore it. But when you're talking about things that are really small, like an electron, you're always going to have some uncertainty as to where it is. You can never say exactly where it is. And so we have to stop thinking about electrons as being like little marbles that are in a specific place at a specific time. We can kind of say, oh, they're around this area, but we can't be sure exactly where they are. And this is where the Bohr model had to get replaced by a theory that wasn't intuitive, wasn't something you could picture easily, was something that didn't necessarily follow the rules we think of. Because you think of an object as being something that you can say, the object is right there, I can say where it's moving. But with electrons, with things that are really, really tiny, they don't actually behave that way anymore. This little cartoon was something a TA found years ago. The guy says, "Oh, Alice, you're the one for me," and she says, this is, I think, her way of letting him down. Like, but Bob, in a quantum world, how can we be sure? There's always uncertainty. I don't know. It's not that great. There's a better Heisenberg joke. Heisenberg's driving along, gets pulled over by a cop, and the cop's like, "Do you know how fast you were going?" He's like, "No, but I know where I am." All right, so great. So a variation on the joke. Cop says, "Did you know you were going 75 miles an hour?" And Heisenberg says, "Thanks for telling me. Now I'm lost." All right. Sure, there's lots of variations on Heisenberg jokes. That's all you need to know about the Heisenberg uncertainty principle, is the fact that it means we have to stop thinking about electrons as being in a specific place at a specific time, that there's something that's going to be more fuzzy. You can't pinpoint them. And so we developed this theory, or I say we, but actually, this was a bunch of mathematicians, physicists, people a lot smarter than I, that developed this theory about 80 years ago. And this theory has been tested over and over and over, and it always passes every test. Every time you do something and quantum mechanics says, all right, this is the way the experiment should come out, quantum mechanics is right. So we just kind of take it on faith, all right, this theory seems to work pretty well. We haven't found anything that contradicts it. But it's really a weird theory. It's not intuitive. It basically says electrons behave in a way that follows these mathematical equations, but they don't behave the way normal things do. An electron can be in one place and then be in another place and not be in between. An electron can theoretically go from one side of this wall to the other side of the wall and back without ever going through the wall. So it can do things that we don't necessarily have daily experience with. So whenever we're dealing with quantum mechanics, you kind of have to let go of the idea that, oh, this should make sense. So it happens to explain a lot of phenomena that occur at the atomic level. It's very difficult to understand, so we'll just take some of the conclusions of the theory and we'll use them. All right, so this is probably the one place in the course where I'm going to say, yeah, it's okay if you don't understand this at a fundamental level. Just take the results and apply them. What it tells us is electrons are arranged in this set of energy levels and sublevels. And they can't be in between energy levels, so they're always going to be in one of these energy levels. Energy levels closer to the nucleus are lower in energy, further from the nucleus are higher in energy. So that still holds true. That's a concept you should understand. So in the first part of the lecture, Mr. Bennett gave some quotes from Richard Feynman, Nobel Prize winning physicist, really interesting guy. A lot of people regard him as the second greatest physicist of the 20th century behind Einstein. He once said, "I think I can safely say that nobody understands quantum mechanics." Now, this is a guy who won a Nobel Prize for work in quantum electrodynamics, which is related to quantum mechanics. So clearly, if anyone should have understood it, it would be him. Another thing he said was, if I could explain it to the average person, it wouldn't have been worth a Nobel Prize. So that one's kind of a cocky statement, but kind of gives you the point. If you really want to understand quantum mechanics, you're going to have to devote your entire life to it. The good news is, some people have devoted their entire lives to it, and then they tell us the important pieces, and then we in this class will just pick out those important pieces and use them. Okay? So, what are some of the things that it does? It's based on the mathematical solution to an equation, right, called the Schrodinger equation. Electrons get described by these mathematical functions. We call them psi, the Greek letter psi. And they're three-dimensional functions. So you're used to functions like f of x, right? You take a function like f of x, you plug in an x value, and what happens? You get out a y value. You get out, a value from the function. That's what a function does. How many people have dealt with like two-variable functions? So like f of x, y. All right. So those kind of functions, you just have two inputs that you put in, and then it gives you a number out. If we want to describe three-dimensional space, which is what we happen to live in, if you want to describe that, you need a three-dimensional function. So psi is going to be a function of three variables. It could be x, y, and z, but it turns out that usually it's better to do it in three different variables. How many people in here have dealt with polar coordinates in math? Maybe a few. Not a lot. R, theta, and phi, that's just three different variables that you can use to describe space. So R is distance from the origin, and then these other two variables are angles. Essentially, you can think of it the same way. It's a three-variable function, and you put in any point in space, and then it spits out a number. All right? And then you take that number that it spits out, and you square it. So there's an extra step there. And that gives you the probability that an electron will be found around that point in space. Let me try and say that sort of in a diagram. All right? And again, this isn't a diagram you need to understand, but it might help you get the idea of how complicated this is. But there are a few of the points in here that we can pull out and use. So we start with the Schrodinger equation. And Schrodinger should have an umlaut in his name. All right, Schrodinger equation, complicated equation. I was able to solve it once, like my junior year of college. I've completely forgotten all that math now. But you start by solving that. And when you solve that, what it gives you is a series of wave functions. So solving this equation doesn't give you an answer. What it gives you is a bunch of functions. All right. So psi of x, y, z. And it gives you a whole series of it. So there's like psi 1s, and then psi 2s, etc. There's a bunch of functions. You get one function, two functions, three functions. Okay? So to give you an example, and you don't have to write this down, the wave function for a 3D orbital, all right? This is an aside. All right. Just for fun. It's the square root of 2 over 81 square root of pi. All right, so far that part's easy because that's just a number. Times z over a naught to the 3 halves times sigma squared times e to the negative sigma over 3 times sine theta, cosine theta. Where rho equals zr over a naught, and a naught is a constant called the Bohr radius. All right. Oh, and z is the number of protons in the nucleus. So if you want to see like a peek down the road, if you choose to study quantum mechanics, this is the kind of thing you would end up dealing with. Like you solve the Schrodinger equation and yield an equation like that, and then, or yield a function like that, and try and make sense of that. One thing I'll point out, function is really, really complicated, except it has a couple of parts. This first part here is just a constant. All of this here, that's just a number, right? Square root of 2 over 81, square root of pi. Z is just the number of protons in the nucleus, so that's a constant number. And A naught is a constant number. So this is just a number out here, out front. And then you have a function in terms of the radius. Function in terms of r, how far you are from the nucleus. And then you have what we call the angular part. So the function out here that's based on angles away from the nucleus. And if none of this makes any sense, that's okay. I just want to give you a little peek into where some of these things come from. And I'll tell you when it becomes important that we reach stuff that you need to know. All right, so you start by solving the Schrodinger equation. All right, that's something we are never going to do. You get this series of wave functions that look like this, these big, ugly mathematical functions, something we're never going to do. Then what you can do is pick one wave function to focus on, and that'll tell you which orbital you're focusing on. So pick one wave function. Because each wave function will describe where an electron is. And so, for example, let's say we pick psi 1s. What you can do with a wave function, since it's a function, you plug in numbers and then you get out another number, right? So you plug in points in space. So you go to a point somewhere away from the nucleus. You put the nucleus at the origin, and then you go to a point in three-dimensional space and plug in the x, y, and z values there, or the r, theta, and phi values there. All right? And that's going to give you a number. Now, in actuality, that this is a complex function. So those of you who've studied maybe imaginary numbers, like complex numbers have a real part and an imaginary part. This is actually a complex number with a real part and an imaginary part. Again, we're not going to do that part. So someone else has done each of these steps for us so far. All right. Then you take that number and square it. And that gives you psi squared. And that's the probability of finding an electron near that point in space. And we're not going to do that either. Someone else has done that. Then the last part is, well, you do that for all of space. You plug in the value for every point in space and you figure out what the psi squared value is at every point in space. And then you're able to construct a map, essentially a map around the nucleus of where there's a high probability of finding the electron and where there's a low probability of finding the electron. Right? So you plug in all points in space. And that map essentially is a picture of what that orbital looks like. So someone else has done all of that stuff for us. What they end up turning out are pictures. And so from this mathematical function down here that's really ugly, you can take that and translate it into a picture. So that particular mathematical function, I'm going to skip ahead a little bit, that particular mathematical function makes this map here. All right, so this comes from that function that I showed you. And what we draw as a picture of an orbital is essentially, all right, this is the region where the electron is when it's in this orbital. It all has this mathematical function underlying it. So I like to give that background. Again, you don't need to understand that. I'm not going to test you on that. But I think it can be really helpful going forward because at some point when we talk about bonding, we will talk about the way orbitals can overlap with each other, and the way orbitals can combine. You can take one orbital and combine it with another orbital. And that's a mathematical process of adding two things. And so it can lend some insight there, and it can lend you some insight when you get to college and you have a professor who, still understands all the math, and talks to you like you understand all the math. If you at least have some idea, okay, there's all this math, and then they plug it in, and then all right, that's where the orbital is coming from. It'll give you a little context to understand it. Because a lot of times professors will just kind of assume, oh, well, yeah, of course you know how to, solve three-dimensional differential equations in spherical coordinates. Why wouldn't you? Because they kind of forget that they're not normal. Are there questions about that process? All right. So someone has gone through this process, and essentially, I guess I could have drawn that picture right here. Essentially, it says that electrons are in energy levels. Levels are split up into sublevels. Sublevels are split up into orbitals. And that word orbital, it's really just like a throwback to the Bohr model. In Bohr, he said they were orbiting. In the quantum model, we're not saying that they're orbiting. We're saying they're somewhere in this area. It's a totally different idea. But an orbital can hold 2 electrons. Can hold up to 2 electrons. And each orbital is going to have a shape that's determined by that underlying mathematical function. So that underlying mathematical function leads to the shape, the picture that we draw. Yep. Oh, great question. So the question was, we say that the map, the picture that we draw, is just a map of probability, and it's saying there's a high probability that the electron is in the space. Is there a low probability that it is elsewhere? Yeah. So theoretically, the probability sort of drops off towards 0 but never reaches 0. So in theory, an electron that's in an atom in my arm, there's a non-zero probability that at any given instant, it's actually in the back of the room. Now that's unlikely, but there's a non-zero probability. So when we draw pictures of orbitals, we kind of cut it off and say, well, this is where there's a 95% probability of the electron being. And that's going to determine most of the properties that it has. But yeah, because it's probability, there's no wall on the outside of the orbital where we say the electron never goes outside this wall. But orbitals are really like clouds. They don't have defined edges. When it's foggy out, or when you're flying through clouds, it's hard to say where the actual edge of the cloud. When you look far away at a cloud, you can see an edge. But when it's foggy, which means there's just clouds near the ground, you can't see a hard defined edge to where the fog starts and where it stops. An orbital is the same way. So orbitals are like clouds. Like probability clouds. They're just densest where the probability is highest, and then they're more diffuse where the probability is lower. So when I tell you that, a d sublevel has 5 orbitals in it, and you're like, well, why does a d sublevel have 5 orbitals in it? I'm just going to say, well, because that's what the math said. The people who went through this whole solving process, that's what they told me. And every single time their work has been checked, every single time they've made a prediction, it worked. So we're going to go with that. But I don't have an answer for, why the energy levels are arranged the way they are, why the orbitals have a shape they are, other than because the math says so, and it works. And so because it works, we'll apply it. But this is the general idea with quantum mechanics. All right, questions about that overview? I think